Ketchups.
And ketchup, right?
Really?
I know, it's so funny, all of a sudden I was like, I did it last year, I should probably make sure something. Yeah, so I'm to figure out and the potatoes. I think we're gonna do some in the post, because we know it's a message last year, so I was thinking like South Gooseberry. Yeah. Yeah.
Pretty good.
Hey, just like my girlfriend. Karma for putting the pink slip on
It's all about karma. I had nothing to do with it.
This thing's recording, isn't it?
How do you feel all right? Otherwise, you're all good.
Yeah. It didn't hurt that bad, to be honest.
That's good.
Surprisingly cheap and slow.
No, I thought it would still be.
This all feels good.
Huh.
Thanks for getting the win for me.
Well, that was all McGuffin.
Yeah.
Slugging.
Josh, don't stick your face.
I realize. Try not to make noise.
All right, might as well get started here. So thanks everyone for coming. This is Molly O'Neill's thesis presentation. So I'll just give a short introduction for Molly and let her take over. It's her show. So Molly comes from Pennsylvania, where she did her bachelor's in science in earth and environmental sciences, and then she actually got a master's in education, in secondary education, at Lehigh as well, before coming here and doing a master's with me. She knew about Oregon. She spent some time at H. Andrews as an undergrad doing some. Actually, no,
I was looking at
Mall. Yeah.
in the Midlands.
In the Meadows. But she, I guess, kind of really likes Oregon and wanted to get back here. When she first came here, she got a degree in earth and environmental sciences, and I think she had an idea of what oceanography was. But it was clear that she didn't exactly know what physical oceanography was, which is what I am and what our lab does. And so it's been a really awesome couple of years seeing her transform from having this vague notion of what oceanography is to like going out every month on Goose Bay, driving the boat around, collecting your observations, and becoming this sort of hardcore CEO and oceanographer. So it's been really amazing. And she can regale you with stories about getting stuck in Goose Bay, and asking fishermen help, people on Coast Road, and other things. I'll let her do that later. I won't embarrass her here. But she has some really neat results, and it's been she's basically taken over the monitoring effort that we've been started in Goose Bay. She'll talk about some of the results from that, as well as what she found out about hypoxia in Goose Bay. So,
All right.
okay.
So
Someone get the lights actually in the doorway. And there are a couple of people joining us on Skype. That's why there's 3 computers up here.
All right. Well, first off, thank you everyone for coming today. I know the summer is usually a busy time for coming and going, so I really appreciate you all being here. So I'm going to get started and talk about my research, which has been on seasonal hydrography and hypoxia in Coos Bay, Oregon. And because I'm going to be talking about this throughout the entire talk, I just want to get everyone on the same page and let you know that hydrography is the study of physical features of a water body, and hypoxia is a condition where the oxygen in the water falls below some threshold value, which is detrimental to organisms. So just so that everybody's on the same page here. And here's a rough roadmap to my presentation, so you all know where we are and where we will be going. Starting with motivation and overview. So in 2012, I got here and I knew that I'd be working in Coos Bay. And I went to this conference in Florence called the Hasita Head Conference, and the topic that year was on oceanography of the Oregon coast. And they were covering some hot button topics like plastics in the ocean, ocean acidification, and hypoxia. And hypoxia really struck me because I had always thought of hypoxia as something that was occurring in the Gulf of Mexico, where you have lots of agricultural runoff spurring these large algal blooms, which then die, sink to the bottom, and draw down the oxygen there. But I had never known that it was becoming such a problem in Oregon. So the setting for hypoxia on the Oregon coast is mainly dictated by this upwelling, downwelling regime that we have here in Oregon. And hypoxia is a natural feature on the Oregon coast because of this. It's where the hypoxia is occurring that's becoming a problem. So to give you an overview of the system that we're in, here in the Pacific Northwest, we have this two-regime system of a low-pressure system sitting over the North Pacific in the wintertime that drives winds to the north along our coast. That northward wind causes an onshore movement of water. Once that water meets the coast, it has to go somewhere, so it goes down, and that's downwelling. This is our wintertime conditions. And the reverse happens in the summer, where you have a high-pressure system, the North Pacific High, migrating to just off the coast of California. That high-pressure system drives winds to the south along our coast. The southward moving wind drives surface waters offshore, and that offshore movement of surface waters needs to be replaced by something, so these water from the deep is pulled up, and that's upwelling. And this water from the deep is naturally lower in dissolved oxygen, or DO, and it's more nutrient rich. And this is just the nature of deep waters in the ocean. When things die in the ocean, they sink to the bottom, where they're decomposed, and that decomposition by microbes draws down oxygen, and it also creates lots of nutrients in those bottom layers of water. So this water coming up onto our coast is naturally lower in DO and has more nutrients. So why is hypoxia becoming worse? Well, we have this current system along our coast. We're part of the California current system, which runs from Baja California up to Washington, where we have the North Pacific current coming in up here, bifurcating, and then you have the California current, which is this thick line going to the south year-round. This second current in here is the California undercurrent, and that's the source of much of the upwelled water. So you have this current moving to the north, and lastly you have a coastal current moving to the south during the summer due to the winds. So low oxygen waters on our coast are not a new phenomenon, it's where they are occurring, which is becoming worrisome. Oops. So they're migrating, this is the natural condition where they're just on the outer shelf. Now we're seeing them moving into the mid and inner shelf. And the reason why researchers think this might be occurring is that the upwelled water is thought to be lower in DO than it has ever been. There's also an increase in upwelling favorable winds, both in intensity and duration. So more upwelling winds facilitates more volume of upwelled water. In that low DO water, you also have more nutrients. Those nutrients drive more respiration, which further draws down the dissolved oxygen. And lastly, you have an increase in ocean temperatures, surface ocean temperatures. So with climate change, we often hear that our atmospheric temperatures are increasing, but it's often overlooked that the surface ocean temperatures are increasing. And what this does is it increases the biological oxygen demand of organisms. It also decreases the solubility of oxygen across the air-water interface. And lastly, it increases stratification in the water column, where your deeper waters are prevented from re-aerating at the surface because mixing is prohibited. So in the literature, you often see values of hypoxia being called at 2 milligrams per liter, but in reality, there's a wide range of thresholds based on the organisms you're looking at and what sort of effects you can expect from those oxygen concentrations. So these plots here show the median lethal concentration for different species of organisms, and this one shows sublethal concentrations where organisms start to suffer reduced growth, less reproduction, forced migration, that sorts of things. And you'll notice that the threshold for those sublethal effects for these three species is greater than 2 milligrams per liter. So just because hypoxia has been set at this threshold of 2 milligrams per liter, there's actually a wide variety of detrimental effects that can occur at different levels. So we're seeing hypoxic waters on the mid and inner shelf. My question is to scale this problem down and see if hypoxia is occurring in Oregon estuaries. And estuary classification is one way of seeing the potential for estuaries to develop hypoxia. So in terms of estuary classification, if you do it by salinity gradients, in an estuary, salinity can be a proxy for density because there's a wide range with the fresh water coming in and meeting the salty water. So salinity is the main driver of density in an estuary, so it's often used to classify different types. In a vertically well-mixed estuary, you have isohalines or lines of constant salinity that are nearly vertical, which means that your water column is well-mixed and the potential for hypoxia is lower because those lower waters can re-aerate easier. In a slightly stratified estuary, you have a little bit more river discharge driving those isohalines slightly. You can see a slight tilt in them. A highly stratified estuary occurs in especially deeper estuaries like Puget Sound, where you have a very deep bathymetry, which allows a large volume of oceanic water to intrude at depth, and you have high discharge. So your isohalines here are horizontal, and that disallows bottom waters from re-aerating at the surface. And lastly, you have a salt wedge, which literally looks like a wedge. Your isohalines are tilted. Mostly occurs in estuaries with high discharge. So knowing what type of estuary Coos Bay is will help us determine whether or not hypoxia is likely to occur there. So if hypoxia were to occur in estuaries, it wouldn't be a good thing. These are just some numbers that I found for estuaries. I want to draw your eye to these last two bullet points. $3.8 billion is brought in each year in commercial fish landings, and 75% of those fish spend some time in estuaries. So imagine the effects, both economically and for the ecosystem, if you have widespread hypoxia in an estuary. You're losing lots of fish and lots of money, so it's not good. All right, so my study site is in Coos Bay, Oregon. It's a 114-mile drive from Eugene. I'd just like to emphasize that, because I've done it so many times, and not always without speeding tickets. Coos Bay is has a large commercial and recreational fishing industry, particularly Dungeness crabs and salmon. And it's a deep draft harbor, which means that the Army Corps of Engineers dredges a main channel through the estuary, along the estuary, to allow large shipping vessels to move in and out. The rest of the estuary is mostly shallow, but that dredge channel is very important for the hydrography of the estuary. Coos Bay is also the location of the Oregon Institute of Marine Biology. Many people don't know that the University of Oregon has a Marine Biology Institute, but we do, and it's located right here. So if you ever want to go down there, it's a nice place. All right, so now on to the objectives of my research. I wanted to know what type of estuary Coos Bay is to help me compare it to other estuaries. I wanted to know how variability in estuary, or what sort of variability there is in the estuarine circulation. And lastly, I wanted to see if there was either a current or record of hypoxia in Coos Bay, and what influences variability in dissolved oxygen levels in the estuary. So, data. I compiled a lot of data for this study. In fact, it almost drove me crazy because I had so much. But it was important to gather not only data within the estuary, but also data from the ocean, the atmosphere, and the land to understand the setting that drives the conditions in Coos Bay. So here's a little schematic to get oriented. So starting with those large-scale data sets, I had oceanic data in the form of mooring that was maintained from 2000 to 2004, just to the southwest of the mouth of Coos Bay. That mooring recorded temperature and salinity of the water, so I could get an idea of the shelf waters that were propagating into the estuary. Atmospheric data came from NOAA buoys that recorded wind speed and direction, so I can understand that seasonal change in wind shifts that occurs in the Pacific Northwest. There was also rain data coming from the North Bend Airport, which is right at that bend in Coos Bay. And lastly, I got freshwater inflows from river gauges that are maintained by the Coos watershed, so I can understand what sort of discharge and river input is coming into the system. In terms of estuarine data, there are several organizations that monitor Coos Bay that have made their data available to us for this study, including the South Slough National Estuarine Research Reserve, which is located down here. It's a federally organized research reserve for the South Slough Coos Bay, which is this lower branch. They have water quality monitors, or water quality loggers that take temperature, salinity, and dissolved oxygen readings at one depth in the water column. These loggers, all throughout the estuary, are located about half a meter above the bottom, so we're getting bottom measurements from these. In addition to the South Slough water quality logger, we partnered with the South Slough in the development of this hydrodynamic model, and in doing so, we deployed this ADCP, which is an acoustic Doppler current profiler, and it measures currents throughout the water column. So that's located about 8 kilometers up from the mouth. And these other loggers are at similar depths to this one, and they're maintained by tribal agencies in the region. So the data that I collected was this along estuary CPD transect, where I would drive down to Coos Bay each month, get in a little motorboat, and go out to the mouth of, well, near the mouth of the bay, and take a CTD transect, or a CPD profile about every kilometer or so. So I'm getting the full depth of the water column. I tried to stay as much in the main dredge channel as I could, so you could resolve all the depth variation. And you proceed up estuary to the main tributary rivers to get a full along estuary picture of what's going on. And just to mention, CPD stands for conductivity, temperature, and depth. I'm sure many of you have already heard this, but that's what our instrument is measuring. It also measures dissolved oxygen, turbidity, and chlorophyll. All right, so now we can go, now that we have all this data, we can look at how, what sort of estuary Coos Bay is. And estuaries have been the subject of research for a long time because they have such an important economic and ecologic value. And researchers have strived to parameterize estuaries so that they can compare them to one another. And this parameterization scheme here, this estuary classification figure, is one of the more recent attempts at parameterizing estuaries. And what it does, on the y-axis here, you have the strength of circulation in an estuary, which is defined by the ratio of the freshwater flow to the frontal propagation speed that can occur from an internal wave due to density differences. The main thing you need to focus on here is the freshwater inflow. That's the main controller of the strength of circulation. The strength of stratification is the ratio